We'll talk about max weight scheduling for ad hoc and peer-to-peer wireless networks. Previously in this chapter of Shrikant and Ying's book, we discussed max weight scheduling for bipartite graphs that occur in switches. Ad hoc wireless networks refer to wireless networks in which devices communicate directly with each other, instead of going through a base station or access point. Nowadays, most wireless access networks, including cellular networks, 5G, 4G, and wireless local area networks, as in Wi-Fi, for example, they are centralized. They tend to not be operating in ad hoc mode. However, ad hoc wireless networks also have a lot of applications as the traditional wireless sensor network structure, vehicular networks, which are emerging and becoming very, very important with vehicular automation, automated driving, and automated roadways. In addition, there are citywide or large area wireless mesh networks, such as mesh networks that are established between gateways. So we have this structure in a ad hoc or network where the network operates in a peer-to-peer fashion. So this device, when it communicates with this device, it has a direct link to it. So in this example, we see all devices communicating with certain other devices. Not all devices necessarily communicate directly with every other device in the network. So this gives us a bunch of links that are available. Each link refers to the availability of a communication channel and a link error control mechanism between a device and another device. And we will not go into routing. We will talk about the scheduling of the use of these links at any given time. Now, let's see. We will model the interference between links as a conflict graph. So we will have a simplifying assumption that two links that interfere with each other cannot be used at the same time. The interference graph basically states which links cannot be active at the same time, cannot be active together. So this is the diagram of the example network, which shows the actual communication links, and this is the corresponding conflict graph. In the conflict graph, each link is represented by a node. For example, link 3 here is represented by this node in the conflict graph. Link 2 is represented by this node. Now, link 2 and link 3 cannot be active at the same time according to, for example, the assumption that this device is not able to operate in full duplex mode, meaning it cannot transmit on link 3 and receive on link 2 at the same time, for example. So this means link 2 and link 3 cannot be active at the same time. In the conflict graph, this is represented by there being an edge between links 2 and 3. Okay, there's an edge between links 2 and 3. This edge means that links 2 and 3 are in conflict. Okay, so the nodes on the graph correspond to links in the actual network. An edge, ij, in the conflict graph represents that links I and j cannot be activated at the same time. Whether links can or cannot be activated at the same time is a result of our underlying assumptions about the medium access layer technology that is used in the actual network. If, for example, our medium access technology was such that we allow two links being used at the same time, for example, as a broadcast link, if we were able to use a broadcast code where this device was transmitting to these two other devices at the same time, then of course the corresponding conflict graph would be different. Or, for example, if we allowed interference, the corresponding conflict graph would be different. But at the moment, we are considering the simplest case where multi-user transmission is not allowed on links that interfere with each other. Okay, but the idea is quite general, more general than that, I just want to add. So now, once we reduce the interference constraints to this conflict graph, then we have the conflict graph to work on. So, now, what is a schedule? As I said, links that interfere cannot be scheduled simultaneously. A schedule, a valid schedule, is a set of links that can be active at the same time without interfering with each other. So a schedule on this conflict graph is a set of links that can be picked to be scheduled at the same time so that the resulting set of links are not in conflict. For example, if I select link 2, this means I cannot select link 3, 4, or 1. But I could select link 5. Once I select link 5, 1, 4, 3, and 6 are not available anymore. So in this example, links 2, 5 would be a feasible schedule. The scheduling problem is the problem of computing a good schedule. What does a good schedule mean? A good schedule depends on the objective of the scheduling problem. If our objective is throughput, for example, a good schedule would be one that maximizes the throughput achieved over time. Now, finding a good schedule, in other words, finding a favorable activation set of links at any time, is the scheduling problem that we will address. Now, suppose the conflict graph has h distinct schedules. Let us enumerate these schedules as m superscript 1, m superscript 2, m superscript capital H. Each of these individual schedules, m, is a vector of size L, and L is the number of links in the network. So L is m is a vector such as, for example, if L is 6, as in the previous example, and I'm selecting nodes 2 and links 2 and 5 in this 6-link conflict graph, then in this my choice of this schedule 2, 5 would be, so my choice of schedule is 2, 5. Let's say m superscript k is 2, 5. M superscript k would be 0, 1 0 0 1 0. Okay, so m sub l superscript h is equal to 1 if link L is in schedule m superscript h and 0 otherwise. So in this context, max wait scheduling refers to the following. At each time instant t, the network schedules the links in schedule m of t at that time t such that m of t maximizes the sum wait obtained over the links in the network selected by the schedule m superscript h. So if you look at the summation consists of summing the entries q sub l for which m superscript h of l is 1, meaning the links that are selected. Now, q sub l here usually refers to the queue size of packets that are waiting to be transmitted on that link. Here's an example. Suppose the queue lengths on the previous conflict graph are as follows. On link 2, the queue size is 5. On link 3, the queue size is 1, etc. So with the previous example I gave, superscript k being 0, 1, 0, 0, 1, 0, the weight of m of k would be 5 plus 2, which is 7. But there is another possible schedule in the same conflict graph that selects, let's see, which one is the maximum? Which one has the maximum weight? Let's select link 4 and link 6. The total weight is 12 plus 9, 21. So apparently at this time, at the current time t, the maximum weight matching at t gives us a total weight 21. Okay, now let's define the set C to be arrival rates into the queues. The queues corresponding to one queue for each link, of course. Rates lambda L such that the total arrival rate into QL is no more than a weighted sum over all the possible schedules, okay, where weights are arbitrary. So if there's a set of weights, lambda h, such that I can obtain this summation, okay, where the set of weights is less than or equal to 1, okay, set C includes lambda L, rates lambda L, that do not exceed this sum. So what does this mean operationally, intuitively? Intuitively it says, intuitively lambda h corresponds to fraction, lambda h corresponds to the fraction of time that the matching, let's not say matching, that the schedule MLH is used. Okay, now I'm free to use any matching for any fraction of time, provided that the fractions of time are not exceeding 1, of course. And let C be the region of lambdas such that the lambdas do not exceed these sums. Clearly, this is a very logical guess for a capacitor region of the network. Okay, and theorem 5.4.1 proves, in fact, that no scheduling algorithm can support an arrival rate vector that's outside of this region C. The proof is very similar to the proof that we did before for the bipartite graph example. Now, because of the P2P structure, our graph is not bipartite, clearly, but the proof idea is very similar. It goes through similar steps. Okay, you can read this from the textbook. Now, perhaps the more interesting proof, but it is not that interesting to us because we've already proved it for the bipartite case, is that max weight achieves this capacity region. More specifically, given an arrival rate vector lambda that lives inside the capacity region, C, the Q size vector is positive recurrent under max weight scheduling. It is positive recurrent, meaning it does not go blow up to infinity. It revisits all finite states infinitely often. This is a certain notion of stability that we used before. So max weight is throughput optimal. The proof is very similar. It follows along the lines that we used to prove optimality of max weight for bipartite graphs before. So I'm skipping the proof, but you can read on it if you wish. Now, here is something that is more general and more important to know. At time instant t, the network can schedule links in the schedule M of t that maximizes a weighted sum of Q. That is not a weighted sum, the sum of weights that are derived from the Q sizes. Okay, this would be called general max weight scheduling, where we are not summing the Q sizes themselves, we are summing some weights derived from the Q sizes. Now, what is a valid weight function? A valid weight function is a function that satisfies the following three conditions. The first condition is the weight is an increasing and differentiable function of its arguments, for the argument x being non-negative, and weight of 0 is 0. Okay. The second condition is the weights go to infinity as their arguments go to infinity. And the third condition is a condition that essentially says the weights do not change too much when the argument is increased or decreased by 1. So given any delta, there exists a constant beta delta such that for any x, 1 minus delta times weight at x plus 1 minus b delta is less than or equal to the weight of x, which is less than or equal to 1 plus delta w x minus 1, of course the positive part plus b delta. So this means that the weight of x is sandwiched between the weight at x minus 1 and the weight of at x plus 1 plus or minus b delta, essentially for any delta this holds. So basically this says that we want our weight function to not change very abruptly when the q size increases or decreases by 1. Okay, so let's see some examples of weight functions that satisfies these three things and therefore are subject to use here in generalized max weight scheduling. For example, you could use W of q equals kappa times q to the m. This is very useful actually. In fact, WQ equals Q is a special case of this. Okay. Note that, for example, when we have Q squared here, we are penalizing high values of Q more, in the sense that we tend to try to give priority to Q's that are larger more than we would if m was equal to 1, for example. Secondly, kappa log 1 plus q for some kappa is also a valid function. This, on the other hand, is a little smoother, is a little, so one of them, so basically this is the case, this is the usual max weights where W of q is q. This is W of q equals alpha q to the m. That penalizes higher, the q's growing more severely. On the other hand, the logarithmic one penalizes q increases much slower, much less than the other two. They will have different properties, obviously. Okay, you may wish to show the validity, by the way, of the above, in the sense that they satisfies these three conditions. Obviously, these weight functions will have a role in how our Q states evolve in the network. The interesting thing is that any of these valid weight functions guarantees optimal throughput. So they are all optimal in terms of throughput. In the proof, in the textbook, this proof is done for Bernoulli arrivals, but many other proofs exist. The original proof is due to Tassoulias and Efremides, which appeared in the Transactions on Automatic Control in 1992 in their seminal paper. So all of these weights correspond to an optimal scheduling algorithm with respect to throughput, but they may result in very different delay properties. If you're interested in further exploring these properties, you can take a look at the following papers. First of all, from back in 1998, Tassoulias has a paper where he looked at different simplified scheduling policies and their properties. In 2004, by Stolyar, there's a paper that analyzes delay in max weights. And finally, not finally of course, but another notable paper is by Mike Neely from 2008. So that essentially brings us to the end of this discussion. In the next lecture, we will talk about, next lecture, we'll talk about QCSMA, which is a distributed algorithm for scheduling in ad hoc peer-to-peer networks.